Let us next consider the stability of floating bodies. Let us consider a fully immersed body and it's floating. So the buoyancy force must be equal to the weight of the force. First, let us consider a geometry or an orientation in which the heavy part of this rectangular body is downwards. So the center of gravity C would be below the center of the body, C as shown, and from this the weight W would be acting. The buoyancy force Fb can be considered to act center of buoyancy B, which is located at the center of the volume. In this case, it is the center of the rectangle. In equilibrium position, the two forces are equal and there is no moment on the body because the weight force and the buoyancy force act in the same line. But if this body is disturbed slightly so that it's tilting to the right, it is easy to see that the weight and the buoyancy force would now produce a couple, and this couple would have a restoring moment because this moment is counterclockwise, which will tend to upright the body. Consider the other case where the body is floating with the heavy and up. The center of gravity is now above the middle point, and if the body now tilts to the right as shown, the weight and the buoyancy form a clockwise couple which will further upset the equilibrium and the body would topple over. Let us consider the ship which is floating in equilibrium in an ocean. There is a weight that acts at the center of gravity, C, and the buoyant force which acts at the center of buoyancy, B. The center of buoyancy is at the centroid of the displaced water. So that is below the waterline, the volume of the water, volume of the ship below the waterline. If the ship tilts to the right, then the volume of the water towards the right is more and the volume of the water displaced is less towards the left, and so the center of buoyancy shifts to the right. Now we see that the buoyant force Fb acting at the center of buoyancy and the weight W acting at the centroid form a couple which is counterclockwise, which will tend to restore the ship back to vertical. This is a stable orientation of the ship. However, we can imagine a situation where if the center of gravity is too high, then the buoyancy center, even if it shifts to the right, but the center of gravity shifts to the right more, and the two forces, the buoyant force and the weight force, form a clockwise couple, which is a toppling moment because it will topple the ship and the ship might turn turtle. To analyze this, Let us consider this simple shape of the ship, where O is at the waterline, C is the centroid. Now, if the ship tilts, B is the original position of the center of buoyancy, B prime is the new position of the center of buoyancy, which is towards the right of B, because there is more water on the right, which is displaced, and less on the left. So there is added buoyancy on the right and lost buoyancy on the left. Because of this, the center of buoyancy shifts towards the right. Let's take a larger view of this. Let's assume the ship tilts through angle alpha. B prime is the new location of the center of buoyancy. B is the old center of buoyancy. Let's determine B, B prime. This is B, B prime. And let's denote it by L. The force FB now acts at the new center of buoyancy. If the center of buoyancy is displaced to a distance L to point B prime, then taking the moment about B, we get FB into L should be the net moment of the additional and lost buoyancies. Added because of the additional buoyancy and moment lost because of lost buoyancy. So, we consider area dA of a strip at the waterline of the ship at a distance y from the center line along the deck of the ship. The additional buoyancy dFB because of this is the density of waters times G times y sine alpha is this height. This distance is y, so this is y sine alpha. Y sine alpha dA is the volume of the gray area, the darker gray area. So this is the additional buoyancy. And the moment it creates is about the point O. This point O is multiply this buoyancy force by F. So dm is rho w g y square sine alpha dA. So the change in moment produced is you integrate this over the whole area of the water line. This additional moment is now found out to be rho w g sine alpha times Ixx, where Ixx is the second moment of the platform area at the water line about the axis of the tilt, that is perpendicular to the screen at point O. This additional moment must be equal to L times the force of buoyancy, which is equal to the weight of the ship. So this is L, which is the distance between B and B prime. The shift in B is rho wg sine alpha Ixx divided by W, the weight of the ship. If we draw a line vertically through B, it will intersect the center line of the ship, which passes through B and O at point M. This point M is termed the meta center of the ship. So this point M, the meta center of the ship, the distance BM plays a very important role It is called the metacentric height. The distance between the center of buoyancy B of the ship in the normal orientation and this point M. Clearly, BM distance is L divided by sine alpha, and so it is rho W G IXX divided by W. This ship would be stable if the center of gravity lies within the segment BM. The lower the center of gravity, the more stable is the ship. If the center of gravity lies above point M, then the ship is unstable. So, while loading a ship, the captain and crew of the ship ensure that the CG of the ship is low enough, well below the metacenter. The metacentric height MB prime is the property of the ship geometry and the weight of the ship. It plays a very important role in flying of the ships. Thank you very much.